why they call me Slim Shady. I'm back. That's why.
What's up, fellas? I'm back to New York from a trip to Ukraine. The trip was amazing. Spent a lot of time with family, friends. It was great. Super excited to get back to the course. I know many of you were waiting for a new lecture and it's finally here. Today we're going to talk about a very popular problem which is called a coin change problem. This is a foundational problem in the world of dynamic programming. Why? Because many other problems resemble variations of this specific problem. So let's make sure we know how to solve it. You know that my lectures are slightly different from the rest of the videos on YouTube, so we are not going to solve the problem and then call it a day, but instead, within the next few videos, we are going to massage this problem, add constraints, change requirements, and so on. I want you guys to feel dynamic programming and not just learn how to solve one-off problems. This is lecture number 12. Let's get started. So, the coin change problem, what is it about? Here is the problem description. Given an unlimited supply of coins of given denominations, find the total number of ways to make a change of size n. So, let's talk about this problem. Let's think about it a little bit. Let's say that in some country, there are the following denominations. 1 cent, 3 cents, 5, and let's say 10. So we have 4 different denominations. Let's try to play with some examples in order to better understand this problem. So let's say we're giving an amount, let's say n equals to 4. How many ways to make a change of size 4? So the first way, we could just use 1 cent, 1, 1, and 1. Use all ones, right? This is one way. The other way, we could just start with 3. We could give 3 cents first, and then we would return 1 cent back. Or we could use third option. Third way is we could start with 1, and then we would still have to return 3. So notice that these two ways are different. The reason why is because I want to solve the simpler variation of this problem first, and in the future we'll talk about another version in which the order matters. Okay, so this is the problem. Now you kind of like better understand what we have to do here, right? So we have to count all the number of ways to make a change. Now, what's the how are we going to solve this problem? Well, we're going to solve it in a typical way. We're going to use the framework, right? So in the first thing we have to do in the framework is to define the objective function. And we can say that f of I equals to the objective function. The definition to the objective function is usually in the problem description itself. It's what we have to do, right? So in our case, f of I, I'm not going to write the entire thing. It will take a lot of space here. But f of I is the total number of ways to make a change of size n, right? So this is the objective function basically. The total number of ways to make a change of size I. Well, the reason why I use I and not n is because f of n is the solution to the problem, right? To the overall problem. So we have to use some other variable in order to, make this difference. So the second step, we need to identify base cases. And when we identify base cases, we want to solve the problem without a computer. We want to solve the simplest possible subproblems. And in our case, we can solve the problem for f of 0. How many ways to make a change of size 0? There is just one way. Why? Think about it. The reason why is because we have to take each coin 0 times, right? And that is one way. Okay, what about f of 1? This one is quite obvious. We'll use 1 cent and give it back. So this is one way. 1 cent. What about f of 2. There is also one way, right? We use 1 cent, and then we still have to return 1 cent, 1 and 1, 2 ones. Let's review f of 3. You see, I don't know the transition function yet. I'm just trying to solve different base cases, the simplest base cases, and maybe I will notice some pattern here. So f of 3. So let's think about the f of 3 now. As soon as you get to a position where you have to slightly think, it makes sense to review it as a separate use case, because maybe it will, show you something. So f of 3, we have the first way to solve this is to use 1 cent first, and then we would still have to return 2 cents, right? Or we could start from 3 cents, we would return 3 cents, and then we would have to return 0 cents. And the more formal way of writing it is f of 3 equals to f of 2 plus f of 0. And the reason why we have f of 2 is because, so here we returned 1 cent, right? We returned 1, and we still have to return f of 2. We still have to return 2 cents. And we need to know the total number of ways to do that. So we use f of 2. We use our function, the objective function. Now, plus, the reason why we have plus is because we have or, either or. And when we have either or, we already talked about it, we use the sum operation because we want to count all the possible ways. And then plus f of 0. In this case, we started from 3 cents and we still have to return 0 cents. So we started from 3 cents. So f of 2 equals to 1. We already know it, right? So this guy is 1. And f of 0 is 1 as well. So 1 plus 1 equals to 2. So there are 2 ways to make a change of size 3. Now, we could write down the sort of like general function here. We could say f of n, and we can see here, right? So we have 2 and 0. So it means that f of n minus 1 plus 3. We had 3 and then 0. So this is f of n minus 3. And this would be a solution, this would be a transition function for denominations 1 and 3. So this 1 here is exactly the coin that we gave back. So like if I would have coins in my hands and I would have to make a change, the coin that I would give you, like this 1, is exactly the coin that I would give you. And then I would still have to return you n minus 1 coins. Then the other way I could give you a change, I could give you 3 cents first, like this 3 cents. It's exactly the coin that I would give you. And then I would still have to return n minus 3, right? Now, since we have more denominations here, the transition function would be slightly longer. So we would have f of n minus 5 plus f of n minus 10. And if you have more denominations, obviously the transition function would be either longer or shorter. One thing that we have to be mindful about here is that when we solve this problem for n less than 10, we have to be mindful about boundaries, right? So like if I would solve this problem if I would apply this function for f of 4, then this guy would end up being -1, like f of -1, right? Which is something we don't want to happen. So this is like when you write code for this stuff, we just have to add some if statements, like if I greater than 5, if I greater than 10, and so on. So this is the solution to this problem, right? The other way to solve this problem, or to get this is basically the transition function, right? And the other way to sort of like devise the transition function is by recalling the climbing stairs problem, where we started to solve the problem from the very end. So like if we were to have 4 cents and if we need to make a change out of 4 cents, like what could be the last coin that we would, we would give away? So we would give away either 1 cent or 3 cents, right? So in this case, we would still have to return 3 cents, and in that case, we would have to return 1 cent. And then how many ways to get 3 cents? We don't know. How many ways to return 1 cent? We may or may not know. And like if you notice that you keep asking the same questions again and again, like you would ask here a question, then it would be like maybe you would return 1 cent here, you would still have to return 2, then in this case you would return 3 cents and you would still have to return 0. So you keep asking like, okay, so how many ways here? How many ways here? How many ways here? It's a hint that you can apply a transition function, right? So in this case, it becomes pretty obvious that the transition function is this one. Okay, cool. So now let's code this problem up real quick. The other quick note here is that the dynamic programming solution is not the most optimal solution. The most optimal solution to this problem is by using generating functions, but this is outside of the scope of this course. All right, so I've got the coin change problem. Given an unlimited supply of coins of given denominations, find the total number of ways to make a change of size n. Let's recall the transition function. It's f of n equals f of n minus 1 plus f of n minus 3 plus f of n minus 5 plus f of n minus 10. So this transition function is for denominations 1, 3, 5, and 10. Let's define our function, coin change. We're given n, the amount, and then we want the number of ways back, integer. Now I'm going to initialize an array that we're going to use as a storage for solutions to our subproblems, and it's going to be of size n plus 1, and the reason why is because we want to return f of n at the very end, so we'll return dp of n. Now we want to specify base cases first. dp of 0 equals to 1, right? Because there is just one way to give a change of size 0. And now we just need to solve all the remaining subproblems starting from 1. So we'll say while starting from I equals to 1 up to n, I plus plus. And now we just need to apply the transition function, right? So we say dp of I minus 1 plus dp of I minus 3 plus dp of I minus 5 plus dp of I minus 10. And as I mentioned before, the problem with this code is that if I would call this thing with an argument, say 4, right, then this guy would end up being -1, and it would, break our program. So we want to take care of this corner cases. So how do we do that? Well, we can just say, basically, we'll take care of every single use case. We'll say if I is greater or equals to 1, then this thing can actually, then we can do dp I minus 1, right? So we can say dp of I plus dp of I minus 1.
And then the same thing we would do for other cases. So for 3, 5, and 10. And we no longer need this guy because we added all of this previous problems like in this code, right? So we can remove that guy. Now, I already have tests for this problem. So let's run them and see if it's working. Yeah, so all is good. Now, one thing to notice here is that I used n-1, n-3, n-5, and 10. But this problem is more like general, like we have to provide denominations. So if we were to provide denominations, we would have another function like coin change with denominations, and we would pass n along with array of different, well, let's just call them coins, array of int. And instead of doing all of that manually, kind of like in this case, we applied 1, 3, 5, and 10, but now these values are inside of coins array, right? So we would have to do something like we would have to go through this array. So we could say for each coin in the coins array, check if I minus coin is equals or greater than 0, then dp of I minus coin. It's essentially the exact same code, but we're using a for loop here so that we could add every single coin. I don't actually have a test for this function, but I'm pretty sure it works. I'll add it after this recording. Cool, that's pretty much it for today, guys. I'll see you in a few days. I'll try to release new episode later this week so that you guys don't have to wait another week for more variations of this problem. As I said, this problem is foundational. It's important to understand it. I want to make sure that you will see different versions of this problem, and it will give you a better understanding of dynamic programming as a whole. Thank you so much, and I'll see you soon. Take care, guys.